Thank you. So good morning, everyone. Welcome to another NL seminar. Thank you for joining us. So today it's my pleasure to introduce Christopher Chu. He is a research engineer working on NLP at DiDi AI Labs. They are located about 500 feet away in the other Marina Tower from the before times. He has a Bachelor of Science in Robotics Engineering, but decided that people are more interesting to talk to than robots. At DiDi, they primarily work on dialogue and translation, but they also branch out into other fun projects like the one we are going to hear about. So again, thanks for joining us, and thanks, Chris. Please help me in welcoming Chris and enjoying his talk. Thank you.
So this talks about applications of NLP to history. And a quick outline before we jump into it, I'll be presenting the work from two papers that were in EMNLP 2020 this year, or last year, I guess, cracking the Wilkinson Code, where we decipher a 200-year-old code and unsupervised Chinese pronunciation, where we develop a method for learning how to pronounce unknown logographic scripts. So first, thank you to my collaborators, Raf, who works for Karga 7, which is a TV production company here in LA, and then Scott and Kevin, who work at DiDi with me. So for a little bit of context, many documents that you see when you're researching history are unusable. They might be encrypted. So the Zodiac's killer sent these encrypted messages to various newspapers in the San Francisco area to taunt them and stuff like that. And some of them had been deciphered. One was recently deciphered in December, but there are a couple outstanding ones. They might be an unknown language or script. So this is the Voynich manuscript, which is a book that was written, it's been carbon dated to the 1400s. The script is totally unfamiliar. There are various drawings of plants and astrological things in it, but nobody knows what the text says. People have theorized the text to be any various languages, anything from like Latin to Chinese even, but we really don't know what it says. Some documents are incomplete or damaged. So this is an example of a tablet. And the problem with stone is it degrades over thousands of years. So you end up missing characters or missing whole words. And then finally, some languages are totally extinct. So this is the Phaistos disc, which is from the Minoan civilization that was on Crete in the around 1800 to 1400 BC. And the civilization was wiped out by a series of disasters, but left behind artifacts that look like this or other things with this writing system on it. But we don't know what language they spoke, and we don't have any idea how to interpret this sort of writing system. So the two papers that I'll be talking about today, one is an encrypted document, and the other one is a method for decoding certain types of unknown languages or scripts. Okay, the first one is cracking the Wilkinson Code. So about a year ago, a TV production company approached Kevin and asked him for some help decrypting some letters. They had a bunch of letters by U.S. Army General James Wilkinson, who was alive around 1800. And here's the little clip from their show.
We've just uncovered that a senior American military general named James Wilkinson was tipping off the Spanish about Lewis's whereabouts with encrypted cipher letters.
We need a code breaker.
We've just uncovered.
Sorry. So they came to us with a bunch of encrypted letters that look something like the top one, and then also some letters that look like the one on the bottom. So the one on the top just has a series of numbers, and the one on the bottom has a series of numbers and words underneath. It turns out that the ones on the bottom are parallel plain text and ciphertext. And the reason that the ones on the bottom exist is probably because during encryption, someone wrote out the letter originally and just left space on top. And then later, either they or their secretary would go back and then encrypt each of the words individually with these numbers. And then finally, the secretary would copy these numbers onto a separate piece of paper, and then they would just mail or send these the ciphertext. So I've transcribed a little bit of it on top here. And it's just these numbers. We can't really read them, but it's nice. We might notice that the numbers in orange are the same. So these documents are parallel versions of each other. From this information, we can do a known plaintext attack, and we can recover the key. Okay, so how much data do we have? Of the ciphertext only, just the numbers, we have 73 pages, and of that, we've transcribed 16. And then of the parallel data, we have 28 pages and have transcribed 8. These numbers aren't entirely comparable because the text is all handwritten, so the text is larger on the parallel pages, and there's twice as much text on the parallel pages, so these numbers aren't quite comparable. Also, some of the pages are partially damaged. They're not full pages, and other ones are not really compatible with the code that we're going to end up using, but I'll get to that a little bit later. All right, let's talk about where this work fits in with other classical codes. So we can have two types of codes and ciphers. Ciphers substitute symbols for each character, and codes substitute symbols for each word. Now, how we generate these symbols or this replacement mapping can vary. So for example, the Caesar cipher uses a simple method. All you do is you take a letter, and to encrypt it, you just shift it 3 places in the alphabet. So B becomes E, C becomes F, etc. For a book-based key, your key would be based on a book. So the Beale cipher, for example, is based on the Declaration of Independence. And in that case, let's say you write the number 100, then the person decrypting it would go look up the 100th letter in the Declaration of Independence, and let's say that's an F, and that's the letter they meant in their message. For codes, where you get these symbols from may vary. It might be a table that you prepare ahead of time, like the Grand Chiffre, or it might come from a book that you've agreed on ahead of time. For example, a dictionary in the case of the Wilkinson Code. Okay, so classical cipher usually refers to things that were used before about World War II when mathematical cryptanalysis became a thing. And the reason we don't use most of these ciphers or we don't use these ciphers for any serious applications anymore is because they leak a ton of information or they're very weak. So the Caesar cipher, it's really easy. To crack it, all you do is you try all 26 possible shifts. For the substitution cipher, which is just you replace each letter with another letter in the alphabet, you can count up the letters. The most common one is probably E. The least common one is probably Q or Z. The U follows the Q, and then you look for common consonant clusters like TH or SH, that kind of thing. For slightly more complicated ciphers, you might need to use a little bit more complicated methods such as EM, but throwing an n-gram character model at it is generally okay, and they can generally be broken. But for codes, the key space is much larger because we have every single word in the English language. So we need more sophisticated tools for this. And that's what we're going to do for the Wilkinson Code. We found a draft of an upcoming book that actually had this quote, which was kind of fun. So far, there are no computer programs for solving codes and nomenclators available. This may change, but in the time being, solving a code or nomenclator message is mainly a matter of human intelligence, not computer intelligence. So of course, our goal is to prove them wrong. Fortunately, in the documents, Wilkinson or somebody else actually included a description of how the cipher works. So we didn't have to reverse engineer this part. And I'll just summarize it here for you. There are two codes actually, the table code and the book code. The table code is based on a shared table between both parties to the message. The table has first a list of proper nouns, so names or places, and then it has an alphabetic section that's about 1,000 words long, and then a list of common words that they probably just forgot to add in the alphabetic section earlier. And the way you use the table code is simply you look up the word if it's in the table, and then you just replace it with the number over here. The book code is actually kind of similar, except instead of using a table, it uses a shared dictionary. And all you do is you look up the word, and then you use the page number, the row number, and the column number, and write those down instead. So you might notice that all of the words in the table section are uninflected. So they're just the base forms of the word. And in a dictionary, the words in a dictionary are usually the base forms in a dictionary as well. So the inflections are not marked. The code actually includes these random letters occasionally, like an N here. And the reason for that is because this 238 is something like be or being, and then adding the N makes it into beam. Also unencrypted are numbers and proper nouns that aren't in the table. Okay, the first step to what we did is the least exciting part of any historic NLP thing, which is transcribing and cleaning the data. Fortunately, the production company did a lot of this for us, so we didn't have to do as much. And I've put the transcriptions of the first part that we saw earlier down here, and the transcription of this one is below. And you can see that it's quite difficult to read, so I've blown up a section of the bottom image on the right. And just reading the numbers off the top, 629, 1078, 752. This one's kind of hard to read, especially given like the ink splotches, and the text is even worse. It says him, the man. But the main reason I know that is because I know that 1078 is the, but good luck reading this sort of squiggle. Yeah, so it's definitely tough to read, and this was initially a source of errors, but we were able to fix some of them by cross-referencing. For example, 1078 appears elsewhere in the text, and also by comparing the top document to the bottom document, we know that the numbers are the same, so we could fix any errors there. Okay, then we split the data we have into a training set and a held out test set, and we build a word bank from the training data. So our word bank looks like the thing on the right, where we put the words we know into this table and just sort them in alphabetical order. This lets us fix any consistency errors, and it lets us fix consistency errors because we know that if the numbers are in order, the dictionary should be in alphabetic order. So we could go back and just double check that any of the numbers that were suspicious were right. And also we did notice that we had one letter that would use a different dictionary because the numbers were out of order. So the first step to deciphering an unknown letter is just to take the words that are in this word bank and replace it with the known word. But what about the unknown words? So let's say we have the symbol 163 and we don't know what it is, but we know it's part of the table code. So we'll find the closest entries in our word bank, A and then we know that this unknown word is about 25% of the way from A. So it's more likely to be the word accommodate than it is to be the word, let's say, alas. Okay, we can quantify this. We chose to use a beta distribution simply because it's parameterized nicely. So it's parameterized by the peak location and the sharpness. The peak location in this case would be the 25% because it's 25% of the way from here to here. And the sharpness is just tuned experimentally. So now we construct a lattice with these possibilities. So first we add the words that we know from the word bank on the right. Then for the unknown words, we'll assign it all the possible words that we generated and give them the probabilities. Next, we'll add the inflections, and we'll divide the probability mass equally over all of the inflections, because recall that the words were not inflected. Then we extract the best path through this lattice using a beam search and GPT. So we're looking for the path that has the highest lattice score because it's closest to the hump in the distribution, and then the best English fluency. So in this case, this sample message would be decoded. He is a general. Yeah, so from the lattice scores, we can determine which of the tokens we're the most confident about. And then we take take those tokens we're very confident about and add them to the word bank. So this word bank will grow every iteration of our algorithm. And as we grow, we add more words in, and then the anchors become tighter. And then we can repeat this until every token is in the word bank. So how well does this method actually work? As a baseline, just applying the word banks, the words we already know, from our training set, we get 41%. and applying the most common word in the lattice. So in this case, let's say gem is the most common word. We would just apply that. It bumps our accuracy to 47%. Then extracting the most fluent path with a beam search, we get up to 73%. We domain tune it on 80,000 words of Wilkinson's letters and get a small bump. We tried more data. We tried another data set of about 3 million words, but because of domain differences, the accuracy dropped. And then finally, once you do this, iteratively adding the decodings, or sorry, iteratively adding words to the word bank, we get another couple percentage points up to 75%. And this is our final number. Oh, I forgot to mention our top line, which is if you pick the best path through this lattice, and by peeking at the actual document, basically, you'd only get up to 91%. And that's because of damaged text or proper nouns that are not in the table. And there's no way we could have recovered those. And finally, I'll note that if we accept words with similar meanings, so for example, a and an, we can get about 80% of the message. So 75% is an exact match and a slightly more or less stringent criteria. We can get 80%. So numbers are great, but what does this actually look like when we're reading a message? So in the table on the right, the leftmost column is the ciphertext, and the second column is the actual decoding, the actual gold standard decoding. So just applying the words that we know, you can see that we have a lot of the common words, which makes sense. Then if you apply the most common word in the most common word in the lattice at each step, you get something that kind of reads strangely. For father of mistress, that makes no sense. To written to you, like it's not grammatical, and it just doesn't really make sense. Then once you add our method, you start getting something that makes more sense and sounds pretty plausible. In some cases, to my ears at least, it sounds more plausible than the gold standard, like requiring every precaution at the end, as opposed to resuming every point. Yeah. Okay. Then another question to ask ourselves is, what if we had more data? So there are two ways to do this. One is to actually, go get more data, but transcribing the data was not fun, and we didn't really want to do more of it. So an easier way to do this is to just generate a bunch of synthetic data. So we took two books by the same author, encrypted both of them, and pretended that we found the parallel plaintext and ciphertext for one of the books, and we only found the ciphertext for the other book. And we varied how much of the parallel data we have. So that's on the amount of parallel data is on the x-axis here, and our accuracy of decoding is on the y-axis here. So we can see that as you get more parallel data, your accuracy improves. But the blue is how much of the accuracy was just from more words being in the word bank, and most of the gain is actually just from having seen more words. It's not from the method performing better and being able to extrapolate better. For comparison, our Wilkinson dataset has about 800 words of parallel text, so we're about here. And remember that our number was about 75%. These numbers aren't quite comparable though, because for the synthetic data experiment, we only used a table code. We skipped the dictionary code and just pretended we had a massive table. But it gets the idea across that most of the gain is probably from increasing the size of your word bank rather than a better method. So finally, we applied our method to text that, to our knowledge, the decoding does not exist anywhere. And by extension, this letter has not been read in 200 years. So James Wilkinson writes, as may tend most powerfully and most directly to dissolve the whole America of the first states from the east and to seize the intercourse of the west. And he goes on. So this is pretty damning evidence that he is colluding with the Spanish crown to interfere with American expansion. Keep in mind that this is from 1800, so America didn't expand all the way to the west coast. So he's trying to interfere with that. And we didn't prime our model with anything about Wilkinson being a traitor to the US or anything about history, apart from what GPT already knows. So to conclude, we develop a known plaintext attack against the dictionary code and achieve 75% accuracy. And finally, we decipher previously unread messages exchanged between James Wilkinson and the Spanish crown. So that concludes this section of the talk. Does anybody have any questions for this part?
So for the part that wasn't the end when you were finding out that he was a traitor, you have the actual completely decoded letters in this case? Was it from some other source?
Sorry, you're referring to this slide?
Just in general, well, you had the Oracle result, for example, and you said that, you know, you could only get up to 91%. So that means because of damage, but presumably that means you know what the actual true text is. I wasn't clear on where that came from.
I see. So we held out some of the text where we did have the true text and used that to evaluate.
Documents? Was that, you mentioned something about parallel text at the beginning, but I wasn't sure if that was truly parallel where you actually literally had the entire text of the letter.
Yes, we do have parallel text for about 8 pages worth of the letter. Of letters.
And then I wondered, so obviously the beta distribution trick only works if you have this notion of the alphabetical code, right?
Yes.
It's not going to generally be true. So what do you think would happen? Could you generalize this technique so that you could still do this kind of like iterative lattice decoding without the kind of really strong signal of the beta distribution? Have you tried doing that? You know, you could do that with a synthetic text, for example.
We haven't tried that. That's one of the reasons I mentioned I had at the very beginning, one of the codes, the grand chiffre is really hard to decipher because that one isn't alphabetic. So we don't have that alphabetic signal. And the reason it's so much harder is just because the state space is so large and there are a lot of plausible decodings. I don't think our method would work for that. Yeah.
I've got another question, if I may.
Sure. Yeah.
So if I understand correctly, the accuracy is basically unigrams, right? It's kind of word by word.
Yes.
Which differs from some classic, metrics like BLEU, which kind of considers n-grams. Also notice that, you get a lot of the function words right, but of course the content words are maybe even more interesting and are not really considered, as important in the metric. Have you considered using other metrics to kind of drive your improvements?
That's an interesting idea. I haven't thought about using BLEU, but that would be a good way to do it.
Yeah.
And yeah, again, this wouldn't be very good for military intelligence because if he said let's attack place X and we don't know where place X is, it's not really useful.
Yeah.
And that's a big concern for using this method. Yeah.
Like for Midway, right? They
yeah, exactly.
Almost 100%, but they didn't know Midway, which was like the one thing they really needed to know. And,
exactly. Yeah.
Yeah. Yeah. And so there's even other metrics that might kind of emphasize content words over function words.
Yes.
To reflect this. Okay, thanks.
That's an excellent point. Thank you. Okay. I'm going to move on to our second half, which is about unsupervised Chinese pronunciation. So in this, I want you to pretend that you're an archaeologist 2,000 years from now in Asia, and you dig up this tablet, and you recognize, oh, I think this might be Chinese, but nobody speaks Chinese anymore. Or sorry, nobody can read Chinese anymore, but people still speak Mandarin. So that begs the question of how would you go about reading this tablet if no one knew how the writing system worked anymore? So this scenario sounds kind of far-fetched, and it is a little bit, but this has actually happened. Linear B, which was also used as a writing system on Crete, was lost when the Minoan civilization collapsed. And it turned out later to be an alternate writing system for ancient Greek. And ancient Greek is still studied today, but we use an alphabetic script. Linear B was a syllabic script. So it was pieced together in the 50s by a couple classicists who found out, first of all, that it was ancient Greek at all, and then second of all, how to read it. And they were able to do this, and now we are confident that we understand the decoding of Linear B. To our knowledge, or to my knowledge, I guess, there are no alternate scripts for Chinese that we don't know about. There is an alternate script called Nushu, which was primarily spoken by Chinese women for several centuries in southern China, but we do know how to read it. So it's not an unknown script. It can also be used to pronounce other dialects of Chinese that also use the standard Chinese writing system, but pronounce things differently. As long as you have a syllable, like a group of people that speak that. So what would a solution to this problem look like? So given a character stream, so this is a set of tablets that we dig up, and a Mandarin syllable stream, so this is the people speaking that we could get from like a radio, let's say, we would want to use some sort of unsupervised analysis to be able to pronounce this character stream, and then also create a mapping between characters and syllables. For people who don't actually speak Mandarin, like myself, here's a quick introduction to the pronunciation. Each character is pronounced with one syllable. And then in this, we're going to exclusively consider Mandarin pronunciation and pinyin, which is the standard romanization scheme. Syllables have one of 5 tones, flat, rising, falling, and neutral. And without tone, there are about 400 possible syllables based on the number of initial consonants you can have and the number of possible codas or ends of syllables. For our experiments, we're going to consider things without tone. Anecdotally speaking to Chinese speakers in our office, they can read they could read a sentence without tone marking. If we just wrote the pinyin out, they could read it, but it might be slightly ambiguous or they might stumble, but they're still able to understand it. So now for Chinese writing. So individual characters, again, pronounced with a single syllable, have rough semantic meaning. So this character here means middle, and this character roughly means weighty, or like it sort of has that meaning, but I don't think you would use it by itself. And then when you combine multiple characters together, so for example, if you combine 中国, you get China, which is literally middle country, or other words like city center that have something to do with the middle, or these words that have something to do with weightiness. I will note that word separators in Chinese are not marked, so a sentence is just a string of characters with no spaces between them. Now digging deeper into individual characters. So this character on top means crow and is pronounced ya. So there are 2 parts to it. The first part, which is kind of on the left, looks like this character here, and that's a hint to its pronunciation because the except for tone, the pronunciation is the same. And the second part is a hint for the meaning because it means bird, and a crow is a bird. So many characters are like this with a hint for the sound and the meaning. And usually the phonetic part is the second component. So for example, this character, the second part is the sound component. But the phonetic components are kind of only hints. So like this, you wouldn't be able to deduce that this means crow from just knowing this. You would know it's a type of bird, but not what type. Or this one's even more abstract, right? Like swollen having something to do with moon. I guess it makes sense because they're both round. But like that's kind of the extent of the similarity there. Also, sometimes the phonetic part only is a hint for the pronunciation. So this character here is made up of our favorite radical that I will use as an example every single time. And the pronunciation part it shares in common is simply the end of the syllable instead of the whole thing. And that's probably because of some pronunciation change over the 2,000 years that this writing system has been around. Furthermore, the general number that's thrown about is if you can read about 3,000 characters, the 3,000 most common characters, you can probably read a newspaper. But there are only 400 possible pronunciations. So therefore, there have to be many characters that are pronounced as homophones and are only distinguished by context. And even with tone, this is also true. But it's even worse without tone. So all 3 of these characters are pronounced the same way. About 10% of characters have more than one pronunciation. So this character can be pronounced one of 2 different ways. And in English, this situation exists, but it's not as common. So for example, the word sight is pronounced is spelled one of these 2 ways. But it's unambiguous in context. Once I say website or eyesight, or I visited the site, you know which one I'm talking about because of just the context. So prior work on this topic has been done. Kevin and Kenji Yamada about 20 years ago worked on this problem and tried to decipher the Spanish, how to pronounce unknown Spanish text, unknown Japanese text, and unknown Chinese text. And they were able to get great results for Spanish and Japanese because Spanish has an alphabet. So there are only about 20 to 25 letters in Spanish, and for Japanese kana, I think there are about 40 or 50 kana. So they were able to get good results on pronouncing text without knowing the writing system. But on Chinese, they weren't able to get anywhere near as good results, possibly because Chinese is such a like there are thousands of characters, thousands of common characters, and even more less common characters. I'll note that they used a different test set from us, and we weren't able to obtain their test set, so we had to run it on our own. And re-implementing that, we get a lower result, probably because we used a larger test set, and they did some tricks like dropping certain characters, and we weren't doing those. So our results are a little bit lower, just re-implementing their system. As a sneak peek, our method gets up to 89%, which is more similar to their results on Spanish and Japanese. And then if you had a pronunciation table, like you had I guess like a dictionary, you would be able to get up to 99%. The reason it's not 100 is because you wouldn't be able to know how to pronounce certain characters, which can be pronounced one of two ways. Okay, so what does our data look like? So remember that we need to simulate digging up a stream of tablets and hearing a stream of syllables that come over, let's say, the radio, or you get from interviews with speakers. So for tablets, we're going to pretend that we dug up all of Wikipedia on stone tablets. And then for the syllable stream, we'll run Baika, which is Chinese Wikipedia. It's owned by Baidu, through an automatic pronouncer, and then use those as our syllable stream. And we'll use the same pronouncer on a set of characters from Wikipedia, but just hold those out as a test set. It's really important to use different sets of characters for the syllable stream and the character stream, because if we didn't, then our algorithm could just take advantage of the fact that Wikipedia has repeated sentences in articles such as like needs citation, or this is a disambiguation page, or things that you commonly see on Wikipedia that are kind of peculiarities of the process there. So even if we're 100% careful about segmenting it and dividing up the test set nicely, it's easier just to use a totally different set of characters from another Chinese language source. So I'll highlight this. The number of tokens we end up using is on the order of hundreds of millions of tokens. Oops. Okay. Nope. For this problem, we use a noisy channel model, which is the exact same approach that Kevin and Yamada took earlier, for which you need a language model and you need a channel model. The language model that we use is going to be a trigram language model. They used a bigram language model. And the channel model will look the same as what theirs did, which is a table from the pronunciation to the character. To solve noisy channel, you use EM. So that's what we did. I'm not going to go over it in detail. It's kind of out of scope of this, but just as a quick recap, it's used to find the maximum likelihood estimate and is a common method. The steps are: you randomly initialize your channel model, you compute your probabilities by summing fractional counts, you adjust these probabilities, and then you repeat the E and the M steps either a set number of times or until you get convergence. So we have the probability of C given P and the C, and Yes, using Bayes' rules, we can break down the probability of the character sequence that we actually observe into the probability of the pronunciation sequence times this is a channel model, and we can use the Viterbi algorithm. And intuitively, we just find the best set of pinyin sequences given this set here. So the intuition is all that we really need to worry about. We tried using character components by replacing the channel model that we think that the previous work used. And instead of just using the character given the pronunciation, we also add components for the first part given the pronunciation and the second part given the pronunciation, and just weight them with some linear combination and then try tuning this. In theory, this would mean that we would only have to learn this term once, for all the characters that share this component, but we didn't see any improvement in accuracy. So to summarize how well this method does, we're able to get 71% accuracy with just this EM decoding. And the only difference from between this and what was done in previous work was that we use a trigram model instead of a bigram model. So this is good, but it's not great. It's not our 80, 90% that we want. So what else can we do? Borrowing an idea from unsupervised machine translation, we can use methods that align character vectors. So we learn fast text vectors for the syllables and for the characters separately. Then we use Muse, which is a library for this. And we learn a rotation matrix to rotate the red space onto the blue space. And then we match each character onto the nearest pronunciation. So that's in figure D. So in this example, I guess the Italian word gatto is mapped onto the English word cat. And you would expect to see that because the spaces look similar, or should look similar, that you can map unsupervised. But we found that this accuracy was very low for our problem, even though it works really well on machine translation. And the reason for that is probably because we have several thousand characters, but we only have a few hundred pronunciations. So our space doesn't look like this. Okay, so instead of doing characters, we do words. So we retokenize the syllables and characters using a segmenter or a tokenizer. I will note that this is standard for Chinese. This system before, when doing translation for Chinese, unsupervised translation for Chinese, you do use words. So we probably should have done this in the first place. And then once you have these, then you have a more similar number of words to words. And then during the matching step, where we match an opinion to a character, we prioritize neighbors with the same number of syllables because we can determine that from just the number of characters and the number of syllables very easily. I will also note that in a truly unsupervised setting where you dug up a bunch of tablets, you wouldn't have these nice tokenizers that exist. So you might have to use something like BPE that works without knowing anything about the language. But for the spoken language, there would probably be a tokenizer you could use. So in summary for the vector method, if you just use characters, you get really low accuracy. But if you use full words, you get much better accuracy. You get 81%. So now we have two methods that are totally independent. We have an EM-based method and we have a vector-based method. Then they agree. Then we can check how often they agree. So they agree in 47% of the time, and when they do, they're extremely accurate. So we can take these high confidence mappings and use these to improve each method. So for EM, we can initialize EM with these mappings. And in the vector method, we can add the constraint. Instead of just making sure they have the same number of syllables, we make sure that the match is consistent with our high confidence mappings. And going back to this, so for EM, we go from 71% to get a 10 percentage point boost to 81%. And for the vector method, we get an 8 percentage point boost by adding these constraints. So this 89% here is our final result. Yeah, so in conclusion, we developed a system that could pronounce Mandarin text without a pronunciation dictionary or parallel resources and achieve good accuracy. And we demonstrate that current vector methods are sensitive to structure, particularly one-to-many problems, leaving an opportunity for designing more robust methods for unsupervised mappings. And that's it. Thank you for listening.
Thanks so much for the great talk. So I think I can now open the floor for questions from the audience. Do we have any questions from the audience?
Can you say some more details about the underlying word type embeddings that you used when in the context of making the Muse mappings, and then also did you use any kind of C dictionary to map between?
For this step, we just use standard fast text vectors on the corpus we had. And so what was?
Do you know how
sorry,
those,
go ahead.
Do you know how those were built?
I don't know the details of fast text, to be honest.
Okay, but I mean, it's fundamentally either a TiVo or a skipgram kind of creation, right? Ultimately.
Yeah. I don't remember which of the two it uses.
But so I wonder if you could speculate. I mean, you have basically two unsupervised approaches for doing some kind of decipherment, right?
Yes.
You know, I'm trying to understand kind of at a fundamental level what the difference is between them. And at least one of the differences seems to be that it seems like, you know, in your traditional EM approach, you're just looking at the prior tokens, right? And so probably for this, it's a centered kind of, it's not a probability, but it's essentially the same information. So I guess I just wondered if, is that it? Is that the only difference? If that's true, could you do EM? Is there a way to do EM where you're looking at forward as well as backward? I guess, yeah, I don't know. Did you get any idea while you're doing experiments if there's some kind of different properties that are being learned by these different methods?
Yeah, that's a really good point. I didn't look into this at all. I don't know if EM has there are any variants on EM that look more into the more forward or backwards. I guess one difference you mentioned is that fast text looks at the whole sentence, whereas EM we were only using trigrams. So this is a more global, or not global, like more sentence level mapping instead of just a very local one.
I don't think it looks at the whole sentence. I think there's a window, but
sure, but I think it's larger than trigram.
Yeah, that's the question, right? Yeah.
But yeah, that would be an interesting thing to look at. Just like which words each one gets correct, and try to figure out why. It might be hard to piece it together, but it would definitely be worth taking a look.
Do we have any other questions from the audience? Okay, I think in that case, we can thank Chris for the very interesting talk. It was very different from the talks that we usually get, and it was really very interesting. Thank you for your time. And I think we can give him a little break before the one-on-one meetings start.
That's good. Thank you.
Thank you so much, everyone. Have a great day.
Bye.